Alright, let's talk about the conditions that favor Sn1 reactions. The reaction coordinate diagram for Sn1 reactions is a little bit different than that of the Sn2 reactions in that you're actually going through two overall steps from beginning to end of the reaction. And in the first step, we mentioned that what has to happen is that the leaving group has to take off. So this CX bond has to break. And the rate determining step is really the point in which the X bond or the CX bond breaks open. The highest energy profile here, the transition state, is that where you have partially begun to break the bond. But once the leaving group takes off and you form this carbocation, you have reached your intermediate. And notice the difference here. Intermediates, reactants, or products are always going to lie on the concave up portion of the diagram. These are things that you can actually isolate or at the very least observe experimentally. The things that we propose that must happen to go from this reactant to that intermediate or from this intermediate to the products is what we call the transition states. These are things that we do not get to see but are the best explanations that we have come up with thus far that explain the experimental evidence. So the carbocation to form the product has to have the nucleophile come in and start forming a bond. And of course, once the bond is short enough, you end up producing a formal covalent bond. And this is the end result of your molecule. So you go through two transition states. The first one has the biggest activation energy. And by far, this is the rate determining step. Even though you still have a different and second activation energy, the second one doesn't really affect anything because it is smaller. If you have enough energy to surmount the first activation energy, then you definitely have more than enough energy to surmount this smaller activation energy, right? So it's not even a question. It's all about the first one, really. All right, so let's think about the nucleophile. Now you might think that here you definitely want to have better nucleophiles, right? Now better nucleophiles means that you're going to be lowering that activation energy by raising the energy of the reactant. But what we find out is that because the nucleophile doesn't actually make an appearance until the second transition state, the one that is not the rate determining step, it doesn't really affect the rate of the reaction. It's just inconsequential, really. And so you really don't change much. Now, that's not to say that you don't want to have like good things to react your molecule with, right? But it's just not going to make a big difference in terms of speeding up your reaction. All right, now the second thing is that in terms of solvent, if you think about your aprotic solvent, what's happening is that aprotic solvents, because now you have that capability of producing very well-defined delta pluses and delta minuses of fair, fair quantity or fair, magnitude. What you can actually do with that aprotic solvent is begin to give an incentive to the leaving group of developing a higher and higher negative charge. And in essence, what this leads to is for the leaving group to break the bond. So these aprotic solvents really make that happen. And on top of that, when you form the intermediate, well, the intermediate can now be solvated by the lone pairs of the solvent, right? So that carbocation can now interact with the lone pairs of the solvent and stabilize it somewhat. And the leaving group can also be stabilized by the positively charged portion of the aprotic solvent. So you get two things here. You get a lowering of the activation energy, thus speeding up the process of the reaction, and you also get a stabilization of the intermediate. All right, so those two things are happening, but by far, the lowering of the activation energy is what leads to a faster reaction. Okay, so aprotic solvents seem to do the trick. Now, what about aprotic solvents? Because aprotic solvents were really good for Sn2 reactions. So what's the deal with them and Sn1 reactions? Well, in Sn1 reactions, the aprotic solvent really doesn't have a good way of interacting with the anion, and the anion is a living group. So because the aprotic solvent is not really good at solvating the anion, it really doesn't put much of an incentive for the living group to take off. And in essence, it just makes it harder because you have nothing here to lower the activation energy. So you just have the worst case scenario. The activation energy is as high as it can be. So the reaction is going to be slower in aprotic solvents. Now, one thing I want to highlight though is that I don't mean to say that you cannot run an Sn2 reaction in a aprotic solvent, or vice versa, that you cannot run an Sn1 reaction in an aprotic solvent. You can certainly do those things, but if you mix match the type of solvent with the type of reaction you're trying to do, you're going to basically take a hit on the time that it takes the reaction to be finished, right? So you're kind of trading that. You could still make Sn2 reactions happen in aprotic solvents, but it's going to take longer. And same thing with your Sn1 reactions. If you want to do an Sn1 reaction, you could do it in an aprotic solvent, but it's going to take a lot longer because the activation energy is not being reduced. All right, now in terms of the substitution at the substrate, unlike Sn2 reactions, in Sn1 reactions, the substrate breaks the bond to the living group first. So the nucleophile isn't even in the picture. But when you break the bond to the living group, you create a carbocation intermediate. And in order to form the carbocation intermediate, the things that will help you is to stabilize that positive charge that not only is present in the carbocation, but that begins to form at the transition state. And what we saw in the previous videos is that the more substitution you have on the carbons, the better you are at stabilizing the positive charge of the electrophilic carbon. And so the activation energy for this bond to break gets lower. It gets lower for secondary compared to primary alkyl halides, and it's even lower for the tertiary compared to the secondary alkyl halides because you have a better method of stabilizing that positive charge on the electrophilic carbon. And of course, once you form the carbocation, the same effect takes place as well. The tertiary carbon is going to stabilize that positive charge a lot more so than the secondary or the primary. So the tertiary is the most stable. And because you are lowering the activation energy the most with a tertiary alkyl halide, the tertiary substrates are the ones that tend to favor Sn1 reactions. So yeah, we have that smaller activation energy overall with the tertiary substrates. And the secondary sometimes will also favor Sn1s. And that's why I was kind of being a little bit ambiguous when discussing secondary substrates in Sn2 reactions because it can go both ways. It can do Sn1s, but it could also do Sn2s. And what's going to really give it away is the type of solvent you're using. You know, you're trying to benefit one reaction over the other. So if you use the solvents to benefit Sn2 reactions, your secondary substrate very well could go via the Sn2 route. If you use protic solvents with your secondary alkyl substrate, then your reaction may very well go via the Sn1 reaction. But the thing that you're never going to see is an Sn1 reaction taking place with methyl or primary electrophile. That is just not good because you don't get enough stabilization with the primary alkyl halide. And with methyl, you get no stabilization, period. So never, ever, ever claim an Sn1 reaction with methyl or primary alkyls. And by the same logic, never claim an Sn2 reaction with a tertiary substrate. All right, now in terms of the living group, regardless of whether this is Sn1 or Sn2, you want the living group to be good. If the living group is crap, then the reaction may not even happen. Or worse yet, a reaction may take place, but it's not the one that you wanted. So the better living group is ultimately going to make it faster for your reaction to go forward, but not for necessarily for the reasons that you're thinking. In fact, here are two ways in which having a better living group helps you in terms of the kinetics of the reaction. First things first, Having a better leaving group means that your bond to the electrophilic carbon is weaker. And if that bond is weaker, then your molecule is not as stable. And that ultimately means that the energy of the substrate is going to be higher. If that energy of reactant is higher, automatically the activation energy is going to be lower. So your reaction is now faster. So that's one thing. The other thing too is that you are lowering the activation energy a little bit by having that better leaving group present, right? So you definitely want to have those good leaving groups. And just to remind you, a good leaving group is one which derives from a strong conjugate acid. So keep that in mind. All right, so comparing the table right here, um, conditions that favor Sn2 from the point of view of the substrate, the first thing you should be looking at, in fact, methyl primary for sure for Sn2, tertiary for sure for Sn1, and secondary will be favored by Sn2 if you use a aprotic solvent. Secondary alkyl substrates will be favoring Sn1 if you use protic solvents. And of course, the nucleophile you want it to be as good as possible for Sn2s. And the leaving group, you want it to be as good as possible. For the Sn1, notice that here I'm being a little bit creative with my definition. The nucleophile is not that you want it to be a bad nucleophile, but because the conditions are that you need to use protic solvent, very often the nucleophile is going to be, moderate at best, a bad one usually. And that's just because of the conditions. Making the solvent protic and creating a carbocation makes it impossible for you to have a nucleophile that is remotely basic, or definitely not one that can be strongly basic. Those things do not coexist. So that's something we're gonna definitely keep an eye out when we discuss elimination reactions in a future lecture. But yes, your nucleophiles are not going to be good. At best, they're going to be moderate, but definitely not strong bases. Strong bases are not nucleophiles you have associated with Sn1s. You could have them associated with Sn2s, however, and that's because you don't generate carbocations in Sn2s, whereas you do in Sn1s. All right, so with all that being said, pay attention for that solvent whenever your secondary alkyl halides or secondary substrates are present. Okay, now the last thing I want to highlight, and I kind of already mentioned it, but it is the fact that when you have um, a nucleophile that is considered a strong base, and to remind you, any any conjugate acid that has a higher pKa than water, the direct conjugate base is automatically a strong base. None of these bases can ever be used in an Sn1 reaction. You just can't, because you have to form a carbocation, and a carbocation is actually a very strong acid. You cannot have both a strong acid and a strong base present in solution at the same time. You're basically hindering the reaction. You're trying to, in essence, kind of change the pKa, go from high pKa to low pKa all at once. It's just not going to happen. So this is the main reason why those strong bases are not really going to play a role in Sn1s. And even if you tried, a different reaction will take place. And we'll talk about that in the future lectures. Now, let's give you an example or two of Sn1 reactions, also known as unimolecular substitution reactions. Okay, so here we have a substrate. The substrate contains a secondary alkyl halide, and the only other thing I'm telling you here is that you are basically mixing this up with water. So water is the other reactant of this reaction. Two things to notice. First thing, the substrate is secondary, but secondly, the second substance, which is going to be the nucleophile, is water, and water is not particularly a good nucleophile. But the other thing about it is that it is protic. You have an oxygen bound to a hydrogen, so this is a protic solvent, and it is a lousy nucleophilic reagent. So this is kind of spelling out Sn1 conditions, right? Secondary alkyl halide, crap base. This looks like an Sn1 reaction. So what's going to happen is that even though this carbon here is chiral, the chlorine is going to take off and it's going to form a carbocation. And when this carbocation is formed, you lose the chirality center. Now the water comes in and attacks, but here is another thing that you have to be careful about. When carbocations are formed, especially if secondary carbocations are formed, you have to look at the nearest neighbors. In particular, you want to see if the nearest neighbor is tertiary or quaternary, right? So if you have 4 different connections to carbon, because what's going to happen is that after you generate the secondary carbocation, we know that tertiary carbocations are better than secondary. So you have something known as a migration. If this happens because you are next to a tertiary carbon, then you're going to have what we call the hydride migration. And what that means is that you're not only moving the H onto this position, you're moving the H with the electron. So this is literally a hydride that is moving onto the carbocation. And when this happens, you rearrange the position of the carbocation. Alternatively, you could have a methyl migration if you are next to a quaternary carbon center. And the end result is that for the hydride migration, you get the hydride to relocate down here, creating the carbocation over there. In essence, you have changed secondary for tertiary carbocation. And down here with the methyl migration, if you move the entire methyl down, well, now you're going to have this methyl there. And the carbocation that used to be here is now on the neighboring center. So in both situations, you have now a tertiary carbocation, which is better than your secondary one. Now, water can actually interact with any of these carbocations, and it attacks with the lone pair. So it goes and attacks the carbocation over here, forming this intermediate. Same thing here, the water can attack the carbocation, forming this intermediate. And notice that I'm using wiggly lines because that represents that the oxygen could be a bolt bond, but it also could be a dash bond. So this kind of tells you it's technically 50-50. And right here, water can also bind, giving you the wiggly, the wiggly CO bond. At the end, the chloride that you have kicked out comes in, removes the proton from the water, right? So it attacks the proton, the electrons go back to the oxygen, and you form your alcohol, right? And I'm gonna keep it wiggly right here because this one in the middle is for sure racemic. This one is not chiral, and neither is this one right here. But you are forming different potential products. So the other thing too is that these products over here and the product over there are the major products because they derive from the most stable carbocations. And in essence, in the majority of these type of problems, I am going to ask you to circle the major product when you do this type of analysis. So be aware of the hydride migrations and the methyl migrations. And what you can see right here is that, wow, we started with one nucleophile, and through the course of an Sn1 reaction, we ended up with 3 different products, 2 of them being the major ones. So Sn1 reactions are not necessarily the best ones to choose from, but if you have no choice and you have to go via an Sn1 route, well, you make do with what you have. All right, so hopefully this gives you a clear idea or a better idea of when to expect Sn2 reactions, when to expect Sn1 reactions. Definitely keep an eye out on that table that I gave you because it's, I think, really makes things very clear. In some cases, I think even better than the textbooks that we have available. All right, so that's it for this lecture. In the next lecture, we're going to talk about elimination reactions. So I'll see you then. Bye-bye.